First, we're going to go through the background knowledge. So the very first stage is the preamplifier, second is the low pass filter, third is the power amplifier, and fourth is the audio amp line out gain control, which can also be a power amplifier. So the very first stage, it picks up the heartbeat sound from the stethoscope acoustic output. Its characteristics is that it has low-level audio signal. The second stage, it amplifies low-level audio signal, boosts to levels suitable for further processing, supplies voltage gain, which is around 10 millivolts to 1 volt. The third, it drives speakers, boosts filtered audio signal, converts small signal to provide audible sound. Last stage, it boosts signals currents to drive speaker to broadcast sound. This whole process is called the signal processing circuit, and it's supposed to process output signal of the microphone to drive speaker. Next, we're going through more in depth of each stage. So this is a negative closed loop op amp. It is an inverting amplifier with a low pass filter. Now it amplifies, invert, and filters high frequency noise. Now why does it amplify? It increases to a more usable level for processing. Now what does a low pass filter mean? So it allows low frequency components to pass. Starting with the first amplifier, the signal passes through this capacitor. Now this is an input coupling capacitor. It blocks DC to let the AC signals through and prevents unwanted DC from affecting its input. After it passes the capacitor, there is this 4.5 volts. Now this is a voltage divider for biasing. It creates a VCC over 2 so that the op amp can process bipolar AC signals using single power supply. Without it, the input would be 0 volts and be clipped in output. Because the signal has no voltage. As it passes through the non-inverting input, it makes its amplifier a non-inverting amplifier. It then passes through and goes to the inverting input. It then goes to this resistor. Now this resistor is a resistive feedback to side gain at low frequency. It then goes to this capacitor, which is a capacitive feedback, and it sets gain drop off at high frequency. Now this paired together is actually an active low pass filter. It attenuates frequency above the cutoff frequency, which is calculated to be around 1.2 kHz. It then feedback to the output. Before that, there's also this resistor and capacitor. Now this paired together is an active low pass filter. This active low pass filter is the same thing, but the cutoff frequency is around 16 Hz. Now why this is an active instead of a passive? It is because it is paired to the amplifier. Why is it a low pass filter for both? Is because the signal goes through the resistor first, making it a low pass. Now to go more in depth into these low pass filters, this first low pass filter controls the high frequency roll off, whereas the second controls the low frequency roll off. These two together makes it a second order active low pass filter. Now why is it not a cascader? It's because both pairs of RC is connected by a single op amp feedback. Now the gain for this is 23. Now both RC pairs are required to work together to shape the gain profile. The RC to C3 pair here sets an impedance to interact with the feedback R2 and C2 over here to determine how the op amp balances its inputs. Even though both RC pairs are low pass in nature, their placement in the feedback network creates a band pass effect. This means the amplifier only boosts signals within a specific frequency range, roughly 16 Hz to 1.2 kHz, which is ideal for capturing the core of the human voice while rejecting unwanted noise outside that range. Moving on from these second order low pass filters, there is this capacitor, which is the output coupling capacitor, which blocks DC so that only AC is amplified. Evidence for the accuracy of 9 volts for the power supply. So this is my patched circuit for my first amplifier. This is my testing point 1 and this is my testing point 2. Now as you can see, my power supply is at 9 volts. My function gen is set to 200 Hz and 200 Mbpp, and then this is my output, the yellow being TP1 and the purple being TP2. And you can see from the bottom of the oscilloscope, my VPP is more amplified compared to the yellow. Same circuit but only a change in frequency of 1 kilohertz instead of 200 hertz, and you can see that the change is actually smaller compared to the 200 hertz because of the increase of frequency, which causes the gain to be smaller and thus making the increase smaller. This is because of the capacitor parallel to the resistor that makes the passive low pass filter, which makes the whole amplifier dependent on its frequency. Next, we have the inverting amplifier here. Here, since the input is inverted, this amplifier will re-invert it back. As the signal passes through, it goes to this 10 kilo ohms. Now this 10 kilo ohms is once again used to calculate the gain. It is paired with this 100k ohms. Now this isn't a normal resistor, as you can see from this symbol. It's actually to notify there is a potentiometer where it can be adjusted. Since it is an inverting amplifier, is a negative, and the R4 is the numerator and the potentiometer is the denominator. Now this adjustable gain is to adjust the strength of the signal. Next, this is another voltage divider for biasing, and this is once again another 4.5 volts for this op amp for it to run so that it isn't 0 volts. So this is my second amplifier showing my inputs, outputs, and my power supply. So showing my 9 volts power supply over here, and also my 200 Hz and 200 Mbpp for my input. Now for my outputs, you can actually see that they are almost similar, input and output, and just that it is inverted because this is an inverting amplifier. Using the same stage, I'm going to be testing out for 1 kHz with 200 Mbpp and also my 9 volts for my power supply. Now you will see later on that the input and output is actually still somewhat similar in voltage, but it's just inverted because it is still an inverting amplifier, just that since the increase in frequency has caused the voltage to slightly become smaller. We're showing how a potentiometer affects the output. So first we'll be using gain when equals to negative RF divided by RG, where RG is the potentiometer. When there's a decrease in RG or the resistance in the potentiometer, it causes the gain to increase and cause more amplification. Whereas when there's an increase in resistance for the potentiometer, the gain will decrease and cause less amplification. Because of unity follower, it is also called a voltage follower. So it's a buffer and it isolates the signal. Now the gain is 1 because there are no resistors at the negative feedback. Now this VCC and ground that is seen in here, and also in here, it is the power which operates the op amp internally and provides current to drive the next stage. Now, this unity non-inverting follower also provides current to drive, which is to explain the low output impedance over here. It also isolates the stage, which explains the high input impedance. Before we move on to the third stage, let's move back. So the input was once like this, then it was inverted. Now the inverted signal goes through this stage and is inverted again. So now you're back to stage 1 with this signal. For the third amplifier, it's actually a Sallen-Key second order low pass filter. So let's go through each component. So as the signal passes through, it goes through the capacitor. Now this is an input coupling capacitor which blocks the DC to let only AC signals through. Next is a voltage divider. It shapes the frequency response, prevents loading of first RC stage, and smoothens the transition between two filtering stages. Now, this voltage is the same with 4.5 volts. Next, the signal passes through this resistor and also is paired to this capacitor. Now, this is another active low-pass filter. It attenuates high frequency above the FC or the cutoff frequency. Next is this pair of active low pass filter. Now the cutoff frequency for this whole amplifier is around 1000 Hz since it is a Sallen-Key second order low pass filter. Now how do I know it's a Sallen-Key? It is because of the feedback from the non-inverting with a capacitor. Now a low pass filter allows only low frequencies to pass through while rejecting all high frequencies. As the lowest frequency can pass through a low pass filter is 0 Hz, the bandwidth of the low pass filter coincides with its cutoff frequency, that is, for the low bandwidth being 0 Hz and the FH being the cutoff frequency. This graph illustrates the frequency response of the Salenki low pass filter. The gain remains flat up to approximately 1.2 kHz, after which it begins to attenuate sharply. This point marks the filter's cutoff frequency. The purpose of this filter is to suppress high-frequency noise and interference that may have passed through earlier stages. As a second-order filter, it provides a steeper roll-off beyond the cutoff, around -40 dB per decade, ensuring that only the desired frequency range is delivered to the speaker. Overall, this stage reinforces the upper limit of the system's bandwidth and contributes to a cleaner, more controlled audio output. This is a good example of a faulty capacitor, especially the ones right before the testing point for the output of stage 3. Usually they help to filter out DC or no noise for the output. This, however, shows that the previous stage had a capacitor problem because it is the input instead of the output. So this is the third stage we're testing for, and it's at 200 Hz and 200 Mbpp. Now, as you can see, the output actually decreased slightly according to the number for the capacitors and the reactor for passive high-pass filter. At the same stage, but the only difference is that the frequency has increased to 1 kHz, and now this increase has affected its output drastically compared to its input because of the passive low pass filter, which causes the frequency to be affected and thus the output to be affected as well. The last stage is the power amplifier, which means that it increases power to drive a low impedance load. Now the signal is finally going to its last stage. So the very first component it passes through is this potentiometer. Now this is a variable voltage divider. It adjusts how much voltage signal passes through. So more signal, which means less frequency for the potentiometer, means that there's a louder output. But if there's less signaling that means that there's a higher frequency for this potentiometer means that there's a quieter output. So the signal passes through here and then it goes through the op amp. So the signal goes through the non-inverting input first and then to the inverting input. Now the pin 4 is ground, so it should be grounded. However, the inverting input is also grounded. Now grounding pin 2 tells the chip to amplify the difference between pin 3 and ground. So pin 3 as input and pin 2 as a steady reference point. The output signal will then go through this capacitor and resistor. Now this isn't a normal active high pass filter because as you can see from the previous stage, this has a connection from the input to the output, and this is the active low pass filter. However, this has no connection to its inputs, it only has a connection from the output and grounds. So this is called the Zobel network, and it flattens the impedance of the speaker load and stabilizes the amplifier. This capacitor has low impedance to ground the high frequency. This resistor short circuits high frequency. Next, the signal will go through this capacitor and it once again blocks DC and amplify audio signal pass to speaker. So for the last stage, it is a power amplifier, so the input output should be somewhat similar. So this is the 9 volts and this is for 200 Hz, 200 Mbpp. So both input output should be in phase and should be around the same values, which over here is around 3 volts. Still at the last stage, the only difference is that the frequency has increased to 1 kHz. Now the input and output should still be in phase. However, because it is an increase of frequency, the input and output has now both decreased together to around 1 volt instead of 3 volts. Now still following the previous stage values.